Hi everybody and welcome back. First off, I would like to apologize for the multiple technical mishaps that we had last week. Canvas changed around some of the settings on the instructor side, and I thought I knew what I was doing, but apparently I didn't. So that's why you guys all got 20 out of 20 on the problem set last week, because I don't want my technical problems turning into problems for you. But hopefully this week will be back to business as usual. So here we are in week 11 of the course. This is where I would normally be starting Unit 3 when the course is in a traditional format, so we would have finished up last week, had a test, and then started with the last bit of material here. And so this last part of the class is all going to be focused around what we're going to talk about today, which is hypothesis testing. And so we'll be learning the logic of it and sort of the idea behind it today and going through an example of a relatively simple version of it. And then once we do that, we're just going to be looking at different versions of this same thing that can tell us different things. So the good news is after this week, everything will start looking pretty similar and pretty familiar, so once you get over the hump of learning this, it usually people usually find that the class gets easier as we head towards the end of the semester. So something to look forward to. All right, so I'm going to start out with the general idea of hypothesis testing here. So I want you to just imagine a judge who's up for re-election somewhere that judges are elected, and who is making this statement. The average person in New Jersey wants robbery sentences to be 15 years long. If you elect me, I'll make that happen. But from last week, we're going to think about the sample that we used to come up with a confidence interval. And we're going to assume that this is a sample that we have. So we asked 100 people how they would sentence different offenses, including robbery. In our sample, we had a mean sentence of 10.6 years and a sample standard deviation of 5.8 years. So we've got two things going on here. One, we have this judge who's saying the average person in New Jersey wants robbery sentences to be 15 years long. Now we're going to say we have a sample of 100 people that we actually asked about this, and we found that in our sample, the average sentence that people would want for robbery would be 10.6 years. So the question is, based on this sample that we took, how likely is it that the judge's statement is true? And in other words, if the average person in New Jersey really did want a 15-year sentence for robbery, how likely is it that we would have asked 100 people and gotten a sample mean of 10.6 years? And what I've just said here is pretty much what we're going to be doing, except a little bit more formally with hypothesis testing. And the idea of hypothesis testing is that you use a sample to test whether something is likely to be true or not in the population. So in this case, the population would just be, people of New Jersey who have opinions on sentencing. And our sample would be the 100 people that we actually ask their opinions on sentencing about. And we're going to use this sample to try to decide whether the judge's statement is likely to be true in the larger population. And specifically, there are 3 steps to hypothesis testing. And as usual, I'm going to go through these in more vague terms here, especially on this slide, and then I'll talk about each of the different terms on the slides, and then I'll go through examples on the document camera afterwards. So if you still have some question marks after this slide, don't worry, we're going to go through it. All right, so 3 steps to hypothesis testing. The first thing that you're going to do are going to be to write hypotheses about what might be going on. And your null and alternative hypotheses are going to refer to statements about things that might be true in the population. Then you're going to find some sort of test statistic based on your sample that's going to help you evaluate whether or not your hypotheses about the population are true. And then, based on that test statistic, you're going to decide how likely or unlikely it is that you would have gotten your sample values and your test statistic given some hypothesis about the population. All right, so let's now take a more specific look at your null and alternative hypotheses. As I said on the last slide, null and alternative hypotheses are statements about things that might be true in the population. So your null hypothesis is just some statement about something that might be true in the population. In this case, we're interested in whether people in New Jersey would prefer a robbery sentence to be 15 years long. So our null hypothesis, in words, might just be that the mean preferred sentence for robbery in New Jersey is 15 years. So it's some statement about what might be true in the population overall. So we're not talking about any samples, we're really just talking about something that might be true in the population. Another way of writing this would be in the form of an equation. And with the kind of test that we're going to be looking at today, you can write it out either in words like this, so the mean preferred sentence for robbery in New Jersey is 15 years, or you can write it out in the form of an equation where null hypothesis is given by that H sub O thing on the left side of the colon, and then your actual hypothesis is that mu, or the population mean, is equal to 15 years. But these both say the same thing, and they both say that in the population overall, the average sentence that people would want for robbery would be 15 years. Your alternative hypothesis is a statement about what might be true if you were to rule out your null hypothesis. So if you were able to say that your null hypothesis wasn't true, what's the alternative? And that's your alternative hypothesis. So in this case, if we were to say that the null hypothesis isn't true, so we're going to take that null hypothesis that the mean preferred sentence is 15 years. We're going to say that's not true. Well, what's the alternative? And in this case, our alternative hypothesis would be the opposite of that, which is that the mean preferred sentence for robbery in New Jersey is not 15 years. So it's the exact opposite of what we're saying might be true in our null hypothesis. Another way of writing this would be using this notation, so in the form of an equation where you have your alternative hypothesis, or H sub A, and then it would be that mu, the population mean, is not equal to 15. So both of these, again, are sort of broad statements about things that might be true in the population. And your null hypothesis is the one that you end up focusing on in the hypothesis test, and that we're going to be trying to disprove with or we're going to see if we can disprove with our sample. The alternative hypothesis is whatever would be true if you were to disprove your null hypothesis. So we're going to be testing whether the preferred sentence for robbery is reasonably, could be 15 years based on our sample. And if we're able to say that it's not likely to be 15 years, then we'd be finding evidence in support of our alternative hypothesis, which is just the opposite of your null hypothesis. And what we're going to be doing in the hypothesis test then is using data from a sample to decide whether to reject the null hypothesis. So we've got this statement about what might be true, that the preferred sentence for robbery in New Jersey is 15 years, and we're going to look at our sample data and see, based on what we found in our sample, is it likely that that's really the true preferred sentence for robbery in New Jersey? And again, if we do end up rejecting this null hypothesis, so if we say that we have evidence that it's not 15 years, then we'd have evidence in favor of our alternative hypothesis, which is, that it's not 15 years. The second part of that hypothesis test, general format, is finding something called a test statistic. And a test statistic is some standardized value that tells where a sample statistic would fall on a sampling distribution. So that's a lot, so I'm going to go through this piece by piece. So first of all, a sample statistic is any statistic that you can calculate from a sample. In today's lecture and in a lot of what we're going to be doing, we're going to be talking about sample means. But there are other sample statistics that you could calculate as well. So an example of another sample statistic would be a standard deviation. But with the test statistic, we're going to be looking at a sample statistic like the mean. We're going to be standardizing it. So we're going to be converting it from whatever units your sample is in into standardized units. And then we're going to see where it falls on a standardized sampling distribution. So your test statistic is just that standardized value. If this sounds a little bit familiar, it's because you've actually already met things that are used as test statistics. And something that could be used as a test statistic would be a z-score. And another example would be the t-score or t-statistic, which are both the same names, or different names for the same thing. And that's what's equivalent to a z-score when you're working with a t-distribution. So these are things that I drew as part of a different lecture that I then took a picture of and put in here. But what these show are examples of a normal distribution and a t-distribution, and what a test statistic might look like. So if you had a sample mean and you converted it to a z-score, your test statistic would be whatever that z value is. If you're working with a t-distribution, and if you remember, a t-distribution is essentially the same thing as a normal distribution, except that it has different shapes when you have different sample sizes, and it's based on an estimation of the population standard deviation instead of a known population standard deviation. But otherwise, it's interpreted the same way, and it works in the same way. So what you have there on the t-distribution would be different t-statistics that you could calculate for sample means that you might get, the probability of getting each one, that's that bell curve. And then if you were to find the t-statistic for that sample mean that you found, your t-statistic would be your test statistic. So again, to sum up on this slide, your test statistic is just any standardized value that you can calculate for a sample statistic like a mean. So you could calculate a z-score, you could calculate a t-statistic, which is just a z-score for a t-distribution, and then you could see where it fell on that distribution. And by where it fell, I mean where it is along the x-axis. So you can see both of these fall kind of towards the right side tail on these distributions that are drawn. That's where the z-score and the t-statistic would fall along the distribution. All right, so I also said that we would be using our test statistic to decide whether to reject the null hypothesis based on our sample. And in order to do this, we're going to be using something called a p-value and an alpha level. The p-value is defined as the probability of getting a sample statistic as extreme or yours or more extreme if the null hypothesis is true. Another way of putting this would be, in a world where the null hypothesis is true, what are the chances that you're going to get whatever sample that you end up ultimately getting? And when it says as extreme or more extreme, that's a way of saying it's either, as large or larger or as small or smaller, but it lets it be either large or small in both directions. So it's just extreme in some direction. And your p-value then is sort of a measure of how different your sample is from what you would expect it to be if the null hypothesis were true. So if your sample mean is much larger than the mean you were expecting, that would be an extreme value, and it would probably give you a small p-value. So it would be unlikely to get. If your sample mean is much smaller than what you were expecting, it would probably also be an unlikely value. And that would be reflected in the p-value as well. The p-value is expressed as a probability, so you'll see it written this way, and if you've read papers for classes that have statistics reported in them, you've probably already seen p-values reported like this. And what that's written as would be, oh, it's not in there. So a p-value of 0.02 would be interpreted as saying there's a 2% chance that you would have gotten a sample statistic as extreme or more extreme as the one that you got in a world where the null hypothesis was true. And the idea behind the p-value is that if you have a low enough p-value, it means that it would be really, really unlikely for you to get whatever sample you got in a world where the null hypothesis is true. And the hypothesis testing logic is based on the idea that if your sample is really, really unlikely given a null hypothesis, you have evidence that the null hypothesis is probably not true. So in other words, if you take a sample, you determine that your sample mean is really, really unlikely, given some null hypothesis. We take the unlikely sample mean as evidence that, that null hypothesis is probably not true. The question then is, how unlikely is unlikely? So if our sample gives us evidence to reject the null hypothesis, if it's a really unlikely sample, we need to decide what that threshold is. So at what point is our sample so unlikely that we say we're going to throw out the whole thing and the null hypothesis probably isn't true? And this is something where it's up to whoever is running the hypothesis test. So it's up to the researcher. And we decide how unlikely a sample has to be by setting an alpha level. And in other words, an alpha level is a threshold for rejecting the null hypothesis. And with the alpha level, you're saying if your sample is, in the 5% of least likely samples you could get if the null hypothesis was true, we're going to say, that's too unlikely, the null hypothesis is probably not true. Or if your sample is in the 1% of least likely samples that you could get if your null hypothesis is true, then we're going to say that's evidence that the null hypothesis isn't true. So if you were to set your alpha level at 0.05 or 5%, you'd be saying we're going to reject the null hypothesis if there's less than a 5% chance that it's true. And common alpha levels in research are 0.05, 0.01, and 0.001. So in other words, it's common in a research study to say whatever findings we get, if there's a 5% chance or less that the null hypothesis is true, we're going to reject that null hypothesis. Or if it's an alpha level of 0.01, we're going to say that whatever findings we get, if they're in that 1% of least likely possible findings given a null hypothesis, we're going to assume that the null hypothesis isn't true. Another common one is 0.001. So that would be if our sample values are, in the 0.1% of least likely samples that you could possibly get given this null hypothesis, we're going to say that's evidence that the null hypothesis isn't really true. And in general, in setting an alpha level, what you're deciding is how easy it is to reject the null hypothesis, and so how strong is your evidence against the null hypothesis. And if you have a larger alpha level, like 0.05, it's relatively easy to reject the null hypothesis. So, you're in your 5% of least likely samples. That means that even if the null hypothesis is true, you're going to be rejecting it 5% of the time, just by chance. And I'll get into that a little bit later as well. With a smaller alpha level, it's harder to reject the null hypothesis because you're only rejecting values that are in this very, very, very small number of possible outcomes. So with an alpha level of 0.001, you're saying we have to be in the 0.1% of least likely outcomes in order for us to take it as evidence against the null hypothesis. So it's harder to reject the null hypothesis because there are fewer possible samples that fall into that very, very small percentage of samples. But if you do reject the null hypothesis, it's stronger evidence against it because it has to be a really, really, really unlikely sample to sort of pass that threshold with a low alpha level. But in a nutshell, and again, we're going to kind of go through all this in less abstract terms soon, but in general, you reject the null hypothesis if your p-value is smaller than your alpha value. So if your probability of getting a particular sample statistic is less than the threshold you've set, we're going to say that we have evidence that we should reject the null hypothesis. And if our p-value is larger than our alpha value, we would say that we don't have any evidence that the null hypothesis isn't true. In other words, our sample is pretty likely to get, even if the null hypothesis is true, so we don't have any reason to reject it, and we're going to fail to reject it. And one point here in terms of the language is that you never say that you would accept the null hypothesis or accept the alternative hypothesis, because the only kind of evidence that we can get out of a hypothesis test like this is evidence against the null hypothesis. But we don't actually get any evidence that's specifically in favor of your null hypothesis. And if that doesn't make sense, just take my word for it. The language to use is reject or fail to reject the null hypothesis. All right, so the kind of hypothesis test that we're going to meet today and that we're going to go through some examples for, along with a little bit more explanation about where some of these ideas come from and how they fit into what we've done so far with sampling distributions and so on. We're going to be doing one that will let us answer the question, is the true population mean equal to some value? And this is also known as a one-sample t-test. And there are 3 steps to the one-sample t-test that should look relatively familiar. The first step is to write out your null and alternative hypotheses. So the first thing you're going to do is write out, one thing that might be true about the world, and then what would be true about the world if we reject that first thing. The next step in the one-sample t-test is to find a t-statistic for your sample mean. So here we're getting a little bit more specific, and we're saying that what we find specifically is a t-statistic. So similar to a z-score, except instead of a normal distribution, it's in a t-distribution. So you're going to find that t-statistic for a sample mean. And you can see now the reason that I introduced the t-distribution last week is that this week we're going to jump straight into using the t-distribution to do stuff with. And there are also versions of hypothesis testing that use the normal distribution, but they're less commonly used, so we're just going to jump right over to the t-distribution here. All right, so that second step is finding a t-statistic for your sample mean. And your third step is that you will use your t-statistic to calculate a p-value that will tell you whether or not to reject your null hypothesis. So with that, I'm going to go over to the document camera, and we're going to talk through the steps of this with some more concrete examples and some more pictures of sampling distributions. And then after that, we'll go through a quicker example that just shows you that the steps that you would need to do to actually solve the problem.